We're working for UPS. Listen, we have a square sheet of paper right there. And that sheet of paper, the area, length times width, happens to be 108 inches squared. We want you to make a box out of it that will maximize the volume. Make an open box that will maximize the volume. So to make a box out of it, I'm going to go and cut like an inch from each side. Well, I'm not sure what the dimension. I'm trying to find out what dimension will make it maximum. But I'm going to cut a piece out of this end. There we go. I'm going to cut a piece out of this end too. Same height. Well. Then I'm going to come in and I'm going to cut these corners out. Oh, don't go. So I took that sheet of paper, the square sheet, I'll show you in a minute, and I'm cutting 4 squares out of the corners. I'm going to fold them along the edges. So there's my paper now. Notice I cut 4 squares. Can you see it? Yep. Now I'm going to fold the paper along these edges, and that's my box. Now what dimension, what height should I make this sheet of paper? And the width and the, well, since that's square piece, that's going to be width and length the same size here. What dimension should I use to maximize the volume of that? Because that's my goal. I want to maximize the volume. So first I need to find the equation for the volume. The volume of a shape like this is what? It's the area times the height. Well, I came in, cut a piece out of the corner here. We have no idea what the length of that piece. Let's call it X. So I got an X out of each corner. When you fold them, the height is X. Otherwise, your box looks funny if it's different height. So what's the area there?
You said you cut 1 inch in on each side, right?
We cut, actually now, I'm changing the whole problem in the book there. So the whole thing was 108 inches squared. Actually, that's not what they're saying. They want the area at the end to be 108 inches squared. We don't know what the dimensions were before, but that's okay. I'm leaving mine the way it is. I misread the question. So what's the width of this and what's the length of that? It used to be unknown to us, right? Let's call that length from here to here S. So what is it from here to there now? Isn't that S minus 2x? You took an x out of this end, you took an x out of that end. This side from end to end used to be what? It used to be S. Same thing, it's a square sheet of paper. S minus 2x. I like my story before. Before I start cutting the corner, I said to you, the area was what? 108 inches squared. Before. That means the length times the width, S times S squared, equals 108. What is S equal to? The square root of 108. Do we know what that number is? So we'll leave it like a fraction. We don't want to use decimal because... So now the volume of this box is going to be S, which is the square root of 108, minus 2x, that's the base, times the height, square it, times x. Now the width, length, whatever, this times that, S minus 2x this way, S minus 2x that way. That's what the square is. Times the height. That's x. And now the question, you want to maximize the volume. When you hear the word maximize or minimize, once you get your equation, you need to take the derivative of that. And if you're going to have min or max, it's always going to be where? at 0. Set it equal to 0. So anytime somebody said to you minimize or maximize, take the derivative of that and set it equal to 0. Well, to take the derivative, I have to use the product rule. The first times the derivative of the second, so dv dx, this is a multiplication. The first times the derivative of x, which is what? 1 plus x times the derivative of the first. That'll be 2 times to the power of 1 times the derivative what's on the inside, which is what? Negative 2. Let's clean it. That'll be 4x and what do you want to do now? Set it equal to 0? Because it says maximize it. When you hear the word maximize, set it equal to 0. Go ahead.
Why are you still calling it dv dx if you have dv dx equals 0?
That's the derivative first. Then it says set it equal to 0.
Oh, okay.
So there's my derivative. Now I need to set that equal to 0. So let's make it 0 equals. And notice if you look at these two, what do they have in common, these two terms? It's one of these, right? So I can factor out. That's one of them. What's left here? I factor, third derivative he's talking about. Calc 2. We're factoring one of these out. What's left? It's this one of them, minus the 4x. Just ugly number. We should start with something nicer, but I misread the problem. I don't want to change it. Now we set each one equal to 0 and solve it. What's x equal to? Let's do the math here. What was, by the way, the dimension, the square root of 108? What was that number? I'm interested in that number. What is it?
10.39.
10.39, 10.4 roughly. Thank you. So when so that means the original sheet of paper was 10.4 this way, 10.4 that way. Let's see, what is x equal to here? What is the square root of 108 divided by 2? Or 5.2 roughly. That doesn't make any sense. You know what that means? There's your box. Take the paper, fold it in half. How is that a box? For this to be 5.2, which is half of that number, the original size, that means you folded the paper in half. Physically, that's not a box. You gotta fold it this way and fold the other one this way. When you cut the pieces, you don't have a box. Because the height of this is 5.2. That means you're going to take it was 10.4 here. You're going to take 5.2 on this end. You're going to take 5.2 on that end. What's left for the width? 0. That's actually your minimum. Remember, we take the derivative, set it equal to 0. That's possible min, max. That's your min. The smallest box. The other one says divided by 4. And if you divide it by 4, what's x equal to?
I think it is 6x minus 6x.
Oh, 6x, thank you. Yep. So the square root of 108 divided by 6?
2.6.
2.6?
Yeah.
So it said make the height 2.6 on this end, 2.6 on that end. Minus 2x minus 4x is minus 6x.
Oh, wait, never mind.
Nope. Go ahead. 1 point something? 1.73?
No. Square root of 108 divided by 6?
Yep.
Yeah, that's what I got, 1.73.
Make sure you close the square root of 108 first.
No.
So the height of the box has to be 1.73. If you want to maximize the volume and you have that much sheet of paper, that's what the height should be. Are we sure that's really a maximum? How do we tell if that's a maximum? We can take the second derivative and see before the 1.73 if the function was increasing, then if it's decreasing. If it was increasing, then decreasing, that's what? Max point. If it was decreasing before that, then increasing, that's what? Min point. I would have used some nicer numbers. I mean, nothing wrong with the question. I mean, I would have just made this like 144 to make it 12 to start with the first example. But I read the question wrong to start with anyway. I probably made it worse. So that's what the dimension that will make the box maximum. Make the height 1.73. That means the width now, again, we cutted these corners out of it. We made the box. So this distance now, it's going to be 10.4 minus twice that number. And this distance is going to be 10.4 minus twice that number. And the height is that number. You make that, you have the maximum box. So you're going to hear in all these sections, maximize, minimize. When you hear that, find the equation for the stuff you want to maximize. In this case, the volume. Find the equation for the volume, then take the derivative of it. Let's try another one. Let me make sure I read this one correctly. We have a picture here. This is what the picture looks like. We have a parabola, concave down. And the equation for the parabola, y equals 4 minus x squared. It says pick a point on the parabola that will give me the closest distance. The closest distance to 0, 2. This is 0, 2. There's a point here, right there. There's one probably matching one here. Find the point that will give me the closest distance to that one. Let me enlarge that picture and just look at one side of it, just so you can show you what we're talking about. I'm enlarging one side so you can see it. This is the 0, 2 here. And there's the point. And we really have no idea what the value, we'll call it x comma y. And you want to minimize that distance, closest distance, that means minimum. So we need to find an equation for the distance. Since it's the closest, that means the minimum, and take the derivative, set it equal to 0. Okay, let's find that distance. What's the distance between 2 points? There's an equation, if you remember, which is what? x2 minus x1 squared plus what? y2 minus y1 squared. That's what I'm going to use. This is x1 and that's x2. This is y1, that's y2. It doesn't matter which one 1, which one 2. I'm using this as 1, that's as 2. So it's going to be x minus 0 squared plus y minus 2 squared. Now in place of y, I'm not going to leave it as y because now I have x and y in the equation. I'm going to replace y by the equation of y, which is what? 4 minus x squared. And there's the minus 2, and don't forget to square it. What's that, 2 minus x squared? And can I FOIL that one? FOIL this, that's 4 minus, is that 4? X squared plus x to the 4th. One more step to clean it. The distance, x to the 4th minus 3x squared plus 4. And you can rewrite that, another way of rewriting that, x to the 4th minus 3x squared plus 4 to what power? 1/2. And remember, the first step is get that equation. We got that equation. We got it. The second step is what? The closest to the point, that means min point. Take the derivative and set it equal to 0. Let's take the derivative of this and set it equal to 0. What's the derivative? 1/2. You got to use the extended power rule, the general power rule. To what power? Negative 1/2 times the derivative what's on the inside, which is 4x cubed minus 6x. Clean it. I can factor a 2 out, but who cares? And now you're going to take the derivative and set it equal to 0. When you have a fraction, you want it equal to 0, that means what? The top of that fraction has to be 0. What value will make that fraction equal to 0? Well, let's factor it. We can take out, what, 2x out of each one? Two x has to be 0, which means x is 0. Obviously, that's silly, because that will put us on top of that point. That will put us right at the point. When x is 0, what's the closest point to this? It says that point. Well, can't be. We're looking for a point on that curvature. It's not. The other one, 2x squared minus 3 is equal to 0, which means 2x squared equals 3, x squared equals 3/2, and x will be plus or minus. We told you there are two answers. The square root of 3/2. One on the right side, one on the left side. Now, if you want to find the y value for them, you plug it in. When you square the square root of 3/2, that's 3/2. The y value will be what? 4 minus 3/2, which is 5/2, I think. So 0, negative 3/2, and 3/2. 0 is not on the line, so the correct answer is negative the square root of 3/2 and positive the square root of 3/2. These are the points that will give you the minimum distance. You wonder why our textbook, almost all the paper that you see here, the size of the book's almost all the same size. Because the publisher don't want to waste any more paper. They don't want to spend money for the paper. So they make the size certain size for the paper. So this example deals with that. Finding minimum area. Then I'll do another one after that. Then we'll go to the next section. Finding minimum area. A rectangular paper containing 24 square inches of print. So we have a piece of paper. This is your paper when you print on a paper. And usually you have margins here. We have margins on the top, the bottom. But the writing area is 24 inches of print, 24 square inches. Now usually the length and the width are not equal. So since they are not equal, let's call this dimension. I'm just going to throw some variables on it. Do I have a red color here? Yes. Let's call this writing area from here to there, let's call it y. And let's call that distance from here to here is x. This is the area of writing on the paper is 24 inches squared. That's x times y. Right? This times that is 24 square inches. That's what it says here. A rectangular page is to contain 24 square inches of print. Here we go. The margin at the top and the bottom of the page, each one is 1.5. So it's 1.5 here the margin, and 1.5 here is the margin. The top and the bottom. And the margin on the left and the right is 1 inches. This is 1. This is 1. What should the dimensions of the page be so that the least amount of paper is used? What are the dimension of the page that at least the least amount of paper? Well, let's look at that sheet of paper now. What is the width of the paper from end to end? Y plus 2. And what's the length of the paper end to end? X plus 3. You want to minimize the area. So area is length times width. X plus 3 times y plus 2. Before you continue with that, we have two variables. With all these problems, we're going to shrink them to one, either both in y or both in x. So how do we change them to either both in x or both in y?
7 equal to y.
Right there. X times y is what? 24. What's y equal to? 24 over x, right? So do that substitution. And I really don't want to use the product rule here to take the derivative. So maybe I'll FOIL this one out. I'm getting tired, it's late now. So x times 24 over x, that's what? 24 plus 2x plus 3 times 24, is that 72? Plus the 6. So if we clean it, that's 2x plus 72x to what power? Negative 1 plus the 30. That's the area, the piece of paper, the size of it. And your goal is what?
To find the
Minimize it. If you're going to minimize it, minimum, that means take the derivative and set it equal to 0. Feel like the commercial. Set it and forget it. Take the derivative, set it equal to 0. What's the derivative? dA dx. The derivative of 2x is what? 2. This will be minus 72x to what power? Negative 2 plus the derivative 30, which is what? 0, and set it equal to 0. Two equals 72 over x squared. Cross multiply. 2x squared equals what? 72. X squared equals 36. X can't be negative. Mathematically, yes, it can be negative, but we're talking about dimension of a piece of paper. So it's 6 inches. Remember, x times y has to be 24. If x is 6 inches, what is y? Y has to be 4 inches. So the pages have to be, for minimizing, 6 by 4. These are the little books that you see ladies at the doctor's office waiting and reading. They like to read these love stories. That's what they're talking about, 6 inches by 4 inches. We use the least amount of paper. It wasn't by guess, let's make the book this big. And I'm sure that applies to our textbook. They know how many square inches of text they want to have there. We can figure the dimension. What dimension will give me that?
Won't the dimension paper actually be 9 by 6?
Oh no, we already had the margin. Oh no, yep, you're right. We didn't add the margin. I thought we added the margin. This is the, no, that was, oh yeah, yep. That's without the margin. No, you're right. We're going to add the margin, yep. I forgot the margin. This is the x, that's before the margin. Now the margin is going to be 1.5 here, 1.5 here, and 1 and 1 on each side. So it's going to be 9 by 6, the paper. So 9 by 6, the outside of the paper. 6 by 4 from the text, the inside of the text there, to give you what you're looking for.
Oh, I think I'm wrong there.
What?
I think the original answer was right. I think I'm wrong. Because we have,
No, that's X and Y, that's the actual text. Remember that picture right here? You're going to add 1515 to it. So that's at 9. Add 1 and 1 to the 4. So y was just the writing here. I'd used the y. So this after the paper is y plus 2, x plus 3. So it is 9 by 6.
I was just curious because when we first used, the first list was x plus 2 and then x plus 3. That's how we figured out. Okay.
Don't get me confused, George. I don't need much help tonight.
Confusing myself.
Another one. I'm going to change the problem a little bit here. This is actually a common practice. It's usually used by chemical engineers digging oil in the field. And usually, I'll make some numbers here. And I have no idea what the answer is going to be. So I'm going to make some numbers, like silly numbers. But you have the ocean there. And we dig an oil in the middle of the ocean. And we find oil right here. There's the oil. We start drilling right there, in the middle of the ocean. Now, we need to get this oil to this location right here. Our office. There's lots of ways we can run the pipe under the ground here. Let's say this is the distance here is 6 miles from the edge of the water, and the distance here is 8 miles. So we can run 6 miles under the ground, under the water, then run the rest of it along the side. Here's the cost. Let's say the cost for doing them under the water obviously is more expensive. It's $50,000 per mile to put these pipes in the bottom of the ocean. I'm sure it's a lot more than 50,000. I'm just throwing some numbers. In the sand, you can bring bulldozers and dig that and put it in. It's not that bad. 30,000. It costs per mile. This is 50,000 per mile in the water. You gotta bring some divers, go on the bottom of the ocean, lay these pipes, make sure it doesn't leak. There's lots of ways to do it. Our goal is to minimize the cost. So maybe I might find there's a way, and again, with the numbers I put in here, I have no idea. Maybe there's a way I can go right to here, then from here go this way. That might be cheaper. So instead of going this way and run it all the way there. You say, why not run it diagonal? Well, if you run it diagonal, that'll be what? What's that distance if you go diagonal? It might be. But if you go diagonal, if this is 6 and 8, that'll be what? 10 miles? At 50,000 per mile? That's 500,000 to run it diagonal. If I run it this way, 6 times 50, that's what? 300,000 plus 30,000 times 8, 24, that's 540,000. That's worse. So maybe I can go like this, maybe that will save me some money. The question is, how far do I want to go? This way and how far this way? Let's call this distance x. Then this piece here, where'd you go? My thick marker. There's my pipe here. I'll make it green this time. Try and save money. Green is money here. What's that distance? We'll call distance 1. We'll call this distance 2. What's distance 1? Isn't that Pythagorean's theorem? It's the square root of what? X squared plus 6 squared, which is what? 36? This 1 squared plus that 1 squared. And what's distance 2? 8 minus x, Jerry. Yep. The whole thing is 8 miles. So from here to there is 8 minus x. The whole thing is 8. Take away x, that's 8 minus x. How much going to cost me? C for the cost. Now distance 1 is going to be underwater. That's 50,000. Let's just write 50K. So the answer is going to be in K, in thousands. I'm not going to put the zeros. 50K times the distance in miles plus along the sand is what? 30K? I'm going to drop the K just right in thousands so we know these in thousands. So that's 50. The square root of that. The square root means what? X squared plus 36 to what power? 1/2 plus 30 times what? 8 minus x. And I could actually multiply this, made life easy on me. What's 30 times 8? 240? Minus 30x. All these in thousands of dollars. That's how much it's going to cost us. So I can sit down, just plug in numbers. I use 1 mile, plug it in, that'll tell me the cost. 2 miles, plug it in, there's the cost. 3 miles, 4 miles, 5 miles. My job is to minimize the cost. Minimize it. Take the derivative and set it equal to 0. What's the derivative? 50 times 1/2. 25 x squared plus 36 to what power? Negative 1/2 times the derivative of x squared plus 36, which is 2x. What's the derivative of 240? Minus the 30. Clean it. 50x over the square root of x squared plus 36 minus 30. Now set that equal to 0.
30x, right?
Nope, took the derivative, right? This is dc, derivative of the cos. So we took the derivative and set it equal to 0. 50x, not k, equals 30. Mathematically, I can grab the 0 out of both sides, right? Divide by 10 to shrink the numbers. Doesn't change the answer mathematically. So cross multiply 3 times and now we got to solve this one. Cross multiply. We did that. That's over 1 here. 5x times 1 is 5x. 3 times that is this one. How do you solve an equation that has a square root in it? Perfect. Square both sides. That'll be 9 x squared plus 36 equals what? 25x squared. 9x squared plus 9 times 36. 324 equals 25x squared. Take the 9 there, that becomes a minus. $324 divided by 16, we said, is 20.25. What's x going to be? Can't be negative here because that's distance. It's the square root of that number. Is it 4.5? If you want to minimize the cost, you want to make sure you run the cable. This is 4.5. You want to run it at this point, then from here 3.5 along this end. And that'll be the cheapest way you can actually have it. This is what chemical engineers do. So you're sitting in your office trying to figure out for them, okay, where should we ship it to? Go through the math, take the derivative, and figure out what number will minimize. Now I use 50,000 per mile, about probably 50 million per mile underwater, deep ocean. Can't send scuba divers down there, go lay this one on the ground there, guys. Okay, don't worry, it's about 3 miles deep there. You'll be fine. Yeah, okay, you have to bring in these heavy-duty machinery, submarines and everything. And when you get leak in it, you saw what happened a few years ago. Yep. We couldn't even shut it off for what, a couple of weeks? That bubbling oil there. So when you hear in this section, minimize and maximize, and the last one I'm going to do